You go. But once again, I really appreciate the invitation, and this is talk with my collaborators. Actually, it's not very new results. It already has some years ago that we finished with this project, but I decided somehow it's maybe the most applied of my jobs. And since the program is also about applied mathematics, I decided to present this talk. Okay, first of all about shape analysis. So actually, what is the idea? What is the shape? The shape, it will be just a simple, smooth, closed curve on the plane, and collection of all these curves called the shape space. Yes, if we have all these curves. So here is just you can see that this is the curve. Yeah. Okay, not all of them homeomorphic curves, but still. Okay. And when we have this collection of the curve, it's infinite dimensional object, and of course it's non-linear. You cannot sum these curves and so on and obtain something. Therefore, the first starting point in the literature was discussing what is the topology behind. If there is topology behind, then probably it's possible to make some manifold structure between this space of curves. So the points on that space is just this kind of closed infinity smooth curve. Yeah, and what kind of category? Is it just continuous manifold, or it could be with some smoothness? If there is some smoothness, then we can start to talk about tangent spaces and so on. And then I come to my lovely topic, geometry. Yeah? Okay, let's go further. Okay, but what we can do with these shapes. And one of the main questions is development or changing of that shapes. Yes? So what is the evolution of one shape to another shape? Yeah? And we are continuing with continuous curves in this space of shapes. Okay? Continuous curves is just one parametric family of continuous map that makes this shape to that shape. Okay? Okay. And then over this space of shapes, we have the space of curves between the elements in that shape. That's what we have. Okay, once we have a curve, then so we somehow can deform that kind of shape to that kind of shape. The question is, can we do it in some sort of the optimal way? There is different ways to do this. Yeah, some of us lose weight very quickly, some of us has the problems. Yeah, so but are there some optimal way? Optimal in what sense? Then you define some functional that you want to minimize or maximize, and then you are asking about curves that minimize or maximize this. So minimize energy, maximize whatever, something else. Yeah. Yeah, the optimal curve usually called geodesic. Yeah, geodesic. And once we have these optimal curves, then we can talk about the distance between points, between these shapes. What is the distance? And then you actually, naturally, we come to the notion of the metric space. Yeah, the points, these shapes, and the distance between them will define it. Yeah? So this is what people were doing quite a lot of time before we entered to that business. And this is some of the initial papers, so where people were trying to define this rigorously, this space of shapes in a different form, in a different approximation. The starting point was really from the applied mathematics, and people were doing this, but then quite strong pure mathematicians were involved in the papers of Nicher and Mumford. There is a series of the papers where they really make the rigorous notion of the space of shapes and analysis on that. Yeah? This is just very top of this huge iceberg of the papers devoted to the development of that topic. But in our talk today, we will be interested in the shapes up to the rotation, translation, and scaling. So if it is square, it is square how you rotate it, how you translate it, or if you scale it, still squared. It's not the circle. Yeah. So that is the shape. So the curve that describes the square is just defined up to these three parameterizations, and probably we will start from the simplest one, from the rotation. Yeah, from the rotation. So first we start to speak about the shapes that are defined up to rotation. Yeah, up to rotation. So this is the same
shapes
shape.
of the whole system up to rotation.
No,
not
no,
rotation
shape,
individual.
shape is this. This heart is a shape. This curve is a shape, but this is the same shape, and this is also the same shape. Shape is just a smooth closed curve. Okay, smooth closed curve. Okay, for the moment in that slide, yeah, but since it is also the the program in complex analysis, so I choose some topic where there is complex variable. Yes. And where it comes from the situation that if we have this curve that encloses simply connected domain, then we can use, and this is on the plane, then of course everyone guessed that now we will use the Riemann theorem and we will parameterize these domains that enclose these shapes, yeah, by some functions. And here the starting point of that process. So we have this shape that was the curve. But for the moment, we are thinking about the domain that enclosed by this curve. Yeah? So this Jordan curve, closed Jordan curve. And we parameterize it in the disk, yeah? In the unit disk. We fix the origin 0 go to 0, 0. We assume that one. And we fix the derivative. We fix the derivative. So all the functions that parameterize this domain will be of that form, yeah. So this function is just a holomorphic function in the disk. They are continuous up to the boundary. Yeah? This will be the main object of our work. Now we made some sort of relation between the shapes that were curves or boundaries of that domains and the domains, and now between the curves and the functions that parameterize the domain enclosed by these curves. So we can work with the shapes, or we can work with the functions. Now we work with the functions in that functional space. And if we talk about the curve that connect to shapes, now it's just, let's say, time depending, or one parameter depending set of functions in that space. Yeah? Clear? Okay, let's go further. And if we start from that process, then the next step, we start from that process, and we parameterize the domain that was enclosed by this curve. Now we will parameterize the domain that outside of that curve. So since the curve is closed, there is two sides, yeah? two components of the connected component. One that contains 0, another one that contains infinity. Yeah? Once we have this map, then immediately we have another one. We have another one that now will be written in this form. And then we do this process. So we have a map, and since everything is closed and analytic, we extend this G across the boundary, and we extend the F also across the boundary. So G and F, after this extension, they defined on that curve. And also they defined in the circle. They not only defined inside of this disk and outside of this, they also defined on the circle. And then we take whatever point on the circle, we come here to the boundary, and then we go back with F, and we end up in another point. So with this composition, we take whatever points, starting from the point on the circle, we end up again in another point of the circle. Let's write it in this form. So what we have, that this composition can be written of this form, where we have this dependence on that parameter theta that would be just an angle here. Yeah. So for any function, what is this process give us? for any function from that space, yeah, the holomorphic functions in the disk that continues up to the boundary, we associated some diffeomorphism of the unit circle. Some diffeomorphism, because if f is given, then g is given. You can find it. No one says that it's easy, but theoretically, we have theoretical part. For any f, you have g, then you make this extension, you make the composition, and you define this f, yeah? This phi. This phi defined up to the, this is just a diffeomorphism, and it is defined up to the rotation since the normalization. Let me show you. So that is the formula, and that is the formula that has sometimes called conformal welding. And this diffeomorphism is that this increasing function, okay, if we want to have the same orientation, preserve the orientation, then it will be just increasing diffeomorphism from 0 to pi to the 0 to pi, but then it has this, okay, this quasi-periodic property, but this is just says you that it's defined on the universal color of the unit. So we have this object, and there is another name for the conformal welding. So the conformal welding is this composition, yeah? And in the more applied papers, they called fingerprints. Yeah, in physics they call conformal welding also, but in vision theory, due to the invention of Mumford and Shah, they call it fingerprints. Okay, so that construction of conformal welding was invented in 60s by Flügger. Yeah, and they call it. There is also another description of that process, like sewing or gluing. It's actually if you have two hemispheres with the circle boundary, and you want to match them in prescribed form, such that the matching map will be conformal in both parts. Then you do essentially the same process. That was described. Okay, and this is just the literature that, for me, it was something useful, where we can read in the more modern language about this conformal welding with the different perspective. Yeah. So this is Finnish school, and this is Russian school. But still, there is this. Now, this is the papers where it was proved. This is Kirillov and Yuri. They were one of the first ones that actually described this conformal welding, elements of the conformal welding, they are isomorphic to that kind of manifold. Okay, here probably I will come to this a little bit later. This object, they are real. Yeah, so they are real objects, but they are isomorphic to the F0. This is the space of holomorphic functions continuous up to the boundary, and it has natural complex structure. So, in order to match these two different structures, so you can consider the complexification of the group of that object, and then take the holomorphic part of that complexified object, and then in this sense it will be by a holomorphic map between F0 that has a natural complex structure, and another one that comes here from the complexification. So everything. So in these initial papers, it's a little bit vague explanation, but then, for example, in Lambert, it's very clearly written all these processes and all the details of the construction. Yeah, Sharon and Mumford, they were first who proposed this conformal welding to use for this analysis of shapes. Yeah, that was idea for parameterization. The first steps were done by them. I will show a couple of pictures that appears there. And then it needs to do some calculations. And here I would like mention the Donald-Marshall with some algorithms that were invented, and some others. Continuation of the use of this conformal welding. Okay, what I'm talking about, so this is the pictures from the book of Sharon, from the paper of Sharon and Mumford, where they related the shape to the diffeomorphism. Yeah? So this is the shape, and this is the function phi that you obtain after this conformal welding, and you have this one. So these 4 points, they correspond to that point, for example, in that picture. Yeah, and this is exactly the Sharon and Mumford, they called fingerprint, sometimes they call diffeomorphism, or it's just the composition. So this is a fingerprint of that picture. Yeah? So, and the question is how you can go from one to another. This is another picture, so this is the shape, and this is corresponding diffeomorphism encoding this shape. And the question how to go, okay, from here to here, somehow it's more natural, because if you know parameterization, then somehow you know what is G, and then you can make this diffeomorphism. The other way around, it was difficult. It is the difficult. Then I was citing, for example, the Donald Marshall, and there is some other papers where really was elaborated some algorithms how to do this, and particularly Mumford was actually aware, so award with this prize for the invention of some of these algorithms and so on. Okay, now a little bit come back to the mathematics. So it was more or less motivation. Now I would like to explain what is the group of diffeomorphisms. Okay. You understand, what is this? This is just a set of collection of orientation preserving maps from the unit circle to the unit circle. If we consider this unit circle like a factor of the real numbers by this now, if so diffeomorphism, we can compose them and we can find the inverse one. So this is what gives you the idea that it has a group structure, algebraic group structure, because this composition is associative operation and this inverse one, and then if it would be finite dimensional collection of the elements, then we would just check that these 2 operations, they are smooth, and we would call it Lie group. Yeah? Now, it's not infinite, it's not finite dimensional object, and then therefore in literature you can find the name that this is Lie-Frichet group. Okay, Lie is just because it's look like Lie, and Frichet means that actually behind of this manifold there is this topological, so topologically it's a Frichet manifold. Yeah, so the topology is defined by the infinite number of the single forms. Yeah, and now, but still, this is smooth object. Okay. In what sense smooth? Here we have to be very careful, because this is infinite dimensional object, and you need to define what is the differentiability in the correct setting, first in the Frichet space, and then with this chart bring it to that non-linear topological space and make it to the manifold glue together and so on. Yeah, therefore I was mentioning here a couple of these works, particularly Kriegel and Michor, this convenient setting of global analysis. Convenient is just convenient for work, and this is actually the analysis. So starting from the like calculus, on the based on the topological space, where you only require that this is locally convex. So any point has a neighborhood that is convex. Yeah, and then there is the notion that it could be made to the complete vector space, such that it was mimic of the Hilbert space or Rn or something like that. But okay, once it exists, this kind of theory, the life became easier. But let's say the physicists, they worked with the Frichet topology without any kind of mathematically rigorous background. Okay, so this is the group, and there is the linearization of that one. That is just a smooth functions with the values not in S1 but in R. If they are in R, then you can pointwise sum them and so on. It's just a vector space. And it's just a vector space. Now, we want to have a manifold and the tangent space at each point. The tangent space at each point will be just isomorphic to that vector space. And to make this function look like vector fields, we just multiply formally by dt. It became within just a vector space, and from the general theory, the group is the global trivializable manifold. What does it mean? It means that the tangent bundle at each point is just a group and a copy of the Lie algebra. That is this vector space. And you know how to move from point to point. Yeah? So that is the good things. Nothing to do with infinite dimension, but here it's also possible to do. Now, this vector space can be made into the Lie algebra once you define the brackets. This is a definition of the brackets. Slightly different, here sign not typical, there is the sign minus. Yeah, okay. If we consider these functions that defined on the unit circle and write them in the Fourier series, and then calculate the this bracket for the Fourier series, then we come to that relations that is known in the literature as a Witt algebra. Witt algebra. Okay? If there is some extension, then it became Virasov algebra. That is so. What we see that this is just a group of diffeomorphism where the Lie algebra is actually Witt algebra. Okay. This is another way. This is another possibility for the studying of these shapes when we study the shapes up to the Möbius transformation. Up to the Möbius transformation, then we start from the parameterizations of the domain that is contains infinity. Yeah, we fix this, make this normalization. This is the same, the holomorphic function defined outside of the unit disk with that parameterization. Then we come with the function that is complementary and now map the inside the disk, unit disk to the domain, make this composition, and we have the elements of that space. Yeah, this function, I will call them G0. Mostly I will work with F, not with G. But elements of here, they belongs to the group of diffeomorphism up to the factored by the Möbius transformation. Okay, so essentially we kill 3 parameters here. That means that we now, so we got to, in that consideration, starting from the motivation and the shape analysis, we come to the 2 homogeneous spaces. Yeah? The group factored by subgroup. The group factored by subgroup. Yeah? If the subgroup was normal subgroup, then this factor would be in another group, and we would be working in the group. That would be the nice situation, but it's not the case. So the rotation and Möbius transformations, they are not normal subgroups. Okay. There is some study behind of this group of diffeomorphism. It's a huge group, but it has only 3 subgroups. It's so few subgroups. It's not typical. Yeah, it's surprising that this is true. And these 2, the most interesting for us, they are not normal subgroups, so we have just another manifold from one manifold that has group structures. Why group structure is useful? You can move in that manifold, right in Rn. We have group structure in Rn, we can go from point to point, and this is commutative process. Okay, the same in the group, but non-commutative. Going forward and back, you do not return to that function, to the same place, but you make some sort of loop and you return. Therefore, a lot of this adjoint map appear that actually encode this way of moving. Okay, yeah. So this manifold were studied actually by Kirillov, Yuriy, in that papers that I mentioned, and they were studied in what sense? They wanted to describe describe some sort of the structure of these manifolds. What is this? What is the metric that is natural there? What is the smoothness of them? What is category and so on? Okay, so for us it's of course comes as granted. And now I'm coming to the main idea where we came with this, why we started to look on that. So the idea was to study the shapes, and shapes lives here. Yeah, do you remember the shapes were parameterized by the diffeomorphisms up to the rotation? So this is our diffeomorphism up to rotation. So they live in this homogeneous space, and we want to find some curve connecting 2 shapes that actually they are connecting to function in that space, and then we would like to find something that is optimal curve. Yeah, minimize some sort of the functional that comes from the nature of distance in time. Okay, so this is quite complicated space because it's homogeneous space, and the idea was that, okay, let us remember that that guy is nothing more than the projection from the group. It's just a quotient space of the group by one-dimensional subgroup. So the idea was, and this is not was exactly our ideas, that's ideas were used in the literature before. So what you do, you look on that curves, and instead of solving problem on this base manifold, you go up and you solve the problem in the good manifold where you can move and where the tangent bundle is trivializable and so on. The calculations can be made at the level of the Lie algebra. The Lie algebra is just a vector space. Okay, so the idea. And then solving problem here, return back. But it needs to be correctly how you move from one point to another. Yes, for any point here, lifting, you have whole subgroup that under this quotient map collapse just to one point. Yeah, one point. Then curve that we connect here have a lot of images. Even if they start from the same point, they can end up in different places. So which one is correct one? In order to, for example, to solve the optimal problem. Which of this one will give you, after the projection, the optimal here? Yeah? Okay, so that is essentially what we have to keep track. And here comes mathematics, or idea, this is the idea of the submersion. Submersion, what is this? This is just smooth map, here in this case from the group of diffeomorphism to this space of functions. Yeah? From the diffeomorphism to the space of functions. So submersion in the sense that for any point you have the pre-image, and moreover it's smooth submersion in the sense that if you take the differential of that map, what do differential? It's take the vector space at this point to the vector space at this point. So point-wise linear map. With linear maps we know how to work, yeah? So if we fix one point here and the image here, and look on the kernel of that linear map, then it will be whole the pre-image, yeah, the pre-image. Because this is just bigger dimension than this one, bigger dimension than this one. Tangent space, we have diffeomorphisms, yeah? And by this linear map, it's mapped to the tangent space at the I of phi. That this is just a function in our space. Yeah. Tangent to. Okay. This is a complex analysis, so this is just something that you always can write in the series finally. Okay, and this for any fixed point, this is a predetermined dimension of this vector space is bigger than this vector space. Yeah, bigger than this. Even if it is infinite dimensional, this is infinite dimensional anyway. There is the kernel. In our case, it will be one-dimensional if we factor by rotation, and it will be three-dimensional if we factor by inverse transformation. Okay, so now linear algebra. Linear algebra. We have one space that is the kernel of that map, and we have the complementary, yeah, the complementary space. So at any point, this guy is decomposed into the sum of two ones: the kernel and complement. Yeah? So the kernel usually called the vector, the vertical space, therefore V, and the complement that is the horizontal, therefore it's H for each. Okay? So now. V, you know how to calculate, but then the complement, there is no metric, there is a lot of complements, yeah? So, and then it's a question how you choose this complement. For physics, for example, when they work in physics with this case, they are working with something that is some minimizing process of the chosen of this H. For example, if by any chance you have some sort of scalar product here, then you can choose the orthogonal complement or some So it depends on the situation. But once you choose this complementary space, yeah, you of course understand that this guy is isomorphic to the tangent space here. Yeah? So this is everything that goes to the zero, and the rest is just isomorphic to that one. So this is two spaces, and instead of work in that space that is quite complicated, we go to that isomorphic copy, that above, and work above on that isomorphic copy, forgetting about V. Yeah? Okay, so this is the idea. Now, since we are thinking about the geodesic optimal curve, yeah, here there is, if there is the metric here, and for us it will be a well-defined metric that was calculated by Kirillov, or there is the Weil-Peterson metric in the case of Nebus transformation and so on. So this is, there is natural metrics here. Yeah? Then what you do, you take a metric and bring it here. Yeah? What is written, what does it mean bring? This is pullback. So you define the metric on H. So if you take whatever two vectors, H1 and H2, that lives here, these guys live here, yeah? Then you just, what is this? This is by definition will be just the metric that you have downstairs. You have here, you know how to take the scalar product. You have your linear map that take whatever element from here and bring it to the tangent space here where this metric is defined. And this is the definition. This is nothing new, this is standard pullback. So having metric here, you always can define it. It's called pullback of that. Pullback of that. Okay, so this is the abstract, the setting that will be exploited in our case. And then what I was saying you that we need just to have the correct lifting, and the correct lifting when you take whatever curve in that space, you look on the tangent vectors. Okay? So we are looking for the curves here. Then you look on the tangent vector to that curve. This object lives here. Then you lift it and bring here. This will be the horizontal lifting. Yeah? The horizontal lifting. So you do not have anything here. If you do not have anything here under the projection, you do not lose information. So this is the correct object that we have to think. Yeah? In order to find the curves here, we will look on the curves here under the condition that that curves have to be in any point have the velocity vector that is tangent to that distribution, not to that. That's it. And this gives you the picture of the geometry with non-holonomic constraints. This is exactly what in geometrical picture. When you start to talk, when you hear non-holonomic mechanics and so on, this is exactly the idea, that you move on the manifold. But your velocity vectors, they are all the time constrained to some subspace. It's not arbitrary curve. It's a curve such that you always respect the velocities that allow to move. Okay. Magnetic field. If there is magnetic field, you cannot move in any direction. Yeah, you have to respect it. And then you have your helixes also, or something like that. Okay. This is the picture that we want. Now we wanted just to calculate something, and here concrete calculation that how we realized this program in the case of the group of diffeomorphisms, the group of rotation, and so on. Okay, very quickly. This is subgroup here. Yeah, subgroup here, not normal but still subgroup. This is subgroup has a Lie algebra. This is just one-dimensional. It's just a Lie group. And what is the Lie algebra? Left invariant vector field is just constant vector field. It's just constant functions. Yeah, constant functions. And how you choose the complement to that? Take this function x that was, imagine that this is just a decomposition into Fourier, and you just kill the constant term kill the constant term. So here you will have all the constant vector fields or constant functions, and here all the functions where you have the first coefficient 0. Yeah? So it's written in this form that this space is just a kernel of that functional that is just integral of the on this period, and if it is 0, it means that there is no free term, no constant term. Yeah? All terms has exponential, and then it gives you 0. Yeah? So, any vector field that, okay, just think that this is written in the Fourier basis starting from the constant in the infinite Fourier series, and here the constant, and here leaves everyone that has constant term 0. Yeah, constant term 0. Okay. And this is object at the level of the Lie algebra. It's just concrete vector space, okay, infinite dimension and so on, but this is just a vector space. But then, of course, it's need to consider that this vector space have to be brought to each point of the group of diffeomorphisms. It's just a copy that made under the translation. Yeah? Okay, this is what I was telling you, that this guy will be isomorphic to that one. So here what we see that this vector space is isomorphic to the tangent space, to the space of holomorphic functions continuous up to the boundary. Yeah? And the Kirillov metric. Okay. What is Kirillov metric? It is exactly the metric that was invented by Kirillov and Yuriev when they were studying these diffeomorphisms factored by the rotation. So if you take this any function in that node space, you write it in the Fourier series at the identity map, yeah, at the identity. So you have this element that is actually from that one. So this is just a tangent vector. Yeah. Once you have this one, okay, write two of this element in the series. In the series, yeah, they start from the n is equal to 0. Yeah. And then the inner product between these two elements, between these two vectors tangent to that one, to the curve, this is the expression for the Kirillov. Yeah. And this is two parameters, alpha and beta. For some of this alpha and beta, the metric actually degenerates. For some of them, not degenerate. So for correct choices of the parameters, it's work quite well. So actually the main idea of that papers of the Kirillov and Yuriev, that they show that there is this two-parametric foliation actually in two-parametric families of the curves, yeah, families of the metrics that we have here. Yeah? Okay, now that is the Kirillov metric, but we need to pull it back under the map H. So this is the result of the pulling back. That is the calculations. Okay, I skip these calculations, but this is result. Now this is the metric on the vector space already here. So the Kirillov metric lives here. This is pulled back. It's live here, right? And this has this expression. This has this expression where D is this one. So do not forget X and Y is just think that this is Fourier series without the first coefficient. That's the element of the Fourier series without first coefficient. And G is just Hilbert transform. Yeah, over now, finally, we get to the calculations. Yeah, so that what probably I was. Yeah, so this is just a slide that summarizes everything. So we have this decomposition, we have the translation, we have metric defined, and we get to that situation that we have the group of diffeomorphism. We know the subspace inside of the tangent space where we have to be tangent, our allowed directions, and the metric. Actually, two-parametric families of the metric. Two-parametric families of the metric. Okay. More or less the same we can do if we have the Möbius, but to define the, so the Möbius transformations, it's three-dimensional subgroup. Yeah, three-dimensional subgroup. Therefore, the complementary part, we have to kill more terms in the Fourier series, and they are given by these kernels of these two functionals. Not only the first one, but the second one. And then everything the same. But in this case, the natural metric is Weil-Petersson metric, that after all this process, pulling back and so on, it's written in this form. It's written in this form. Fourier transform, and this is the elements, but now this x and y, they are, if you decompose into the Fourier series, they do not have the first term and they do not have the second one, because they are on this complementary part, on the complementary part here, after you kill the first and the second. Yeah, now, so we can calculate this, everything, and the idea was to find the geodesic. We minimize the energy functional, yeah, this is just an energy functional. G is bilinear form, our metric that we calculated, but that curves, they are such that they are not arbitrary, they are such that they all the time tangent only to that one, not arbitrary. Okay, great. A little bit more calculations. So we minimize this energy functional, and now let's come to the classical variational problem. Yeah, we need to have a family, yeah, that have a fixed point, and then we calculate the minimum in this family of curves that go from one point to another. Yes, and infimum will be the geodesic. It's just variational calculus, classical one. Yeah, but it's not just for fun. It's a long story behind, because everything works more or less like in the finite dimensional case if you're working in the Hilbert space or if you're working in the Banach space. If you go to the Fréchet space, then you do not have the inverse function theory, and then you do not have this kind of the object or instrument that you can work. But the calculus, this calculus somehow survived. Yeah? So, once again, so we construct this parametric family. Yeah? So for any curve, we consider the family, the curves, such that they are fixed at the beginning, at the end, and yeah. And for the second parameter, when s is equal to 0, you are exactly in your curve. All others, you just around. Yeah? So choose a curve. This is your gamma of t. Then you can see that whatever other ones, and this, any point here, is just parameterized by 2. So this is change of parameter s, and in that direction, change of parameter t. Yeah? There is, for given curve, you form the parametric family. That was the parametric family. Yeah. And it's like in the classical variational calculus, but the problem is that all these curves, they have to obey the same rule, that the tangent vector all the time have to be here. You cannot consider, even in that variational family, again, any tangent vector, it should be in this H space, into the H space. So it's horizontal variation family. And this is clear. This is logical. Now we have to just find the variational derivative of that functional and look where it is 0. If it is 0, for that curve where this functional is 0, we will say that this gamma is optimal. Yeah? It's classical Fermat theorem. Yeah? If you have minimum, the derivative will be 0. That is what is happened here. Great. But here comes difference between the classical variational approach and the non-holonomic situation. That is, okay, nothing to do with infinite dimensional, even in finite dimensional, the same idea. So if we have variational family, then we can consider the vector field that says you how your curves spread. Yeah? So this is just a tangent vector in that direction. In the direction of S. Given variational family, we can define this vector field, variational vector field. But if you have, again, just a given curve, yeah, you always can only consider the vector fields along this curve such that at the beginning and at the end they will be 0. Look, this variational vector field, yeah, it says you how spread your family in this S direction. But what's happened here? Nothing is spread. So this guy is just 0 here. Okay? It's just 0 here. So it says you that any element from here, it's actually belong to that one. Because this Z, they have nothing to do with variational family. It's just whatever vector fields, yeah, such that they start from the 0, 1, then they start to increase, and then when you come here, they again 0. Yeah? If you have variational vector field, then it will satisfy to that one. So what we see that these spaces belong to that one. This space belongs to that one. Marvelous things, and the core of the Riemannian geometry, not trivial theorem that they are coincide actually. One of them is nothing to do with variational family, and apparently you can forget about the variational family and work only with that kind of vector fields. And this is the marvelous things in the variational calculus, in the with the absence of these constraints. If you have constraints, it's not true. There is some curves where you definitely have this gap. Okay? So there is two types of curve. When you have coincidence, like in the classical case, and when you have that this variational family of vector fields is a proper space. Okay, there is two types of curve, and they lead to two types of the geodesics. One of them called normal. Guess which one? The same as in the usual case. And another one is called abnormal. We will concentrate on the normal. Okay, there is a whole study in that non-holonomic geometry where they try to describe how many of these guys and how often this guy can be a real geodesic. And what is surprise? It can be. Not very often, but it can be. There is rare cases when this guy became realized the shortest distance. Okay, but this is another story. Okay, and now, okay, let me, in 5 minutes to finish somehow. What we do, we just take whatever curve. This is the derivative, yes, this is derivative, the velocity vector. And since I told you that the advantages of the working in the Lie groups, that you can bring everything to the real, just to the vector space. You do this, and you do not work with the vector field that change from point to point. You just work with the curve that live in the vector space. So you come to the classical analysis in, let's say, Rn. Why? Because you have a group. You cannot do it in the meaningful, but in the group you can do it. This is why it was idea to bring everything to the group and then start to calculate. Okay, this is the theory. So if we have formulated in a general setting that we proved, so the K is group of rotation, yeah? But if there is a subgroup of the bigger group, yeah, and you have the decomposition of the Lie algebra, so this is just the Lie algebra K. So it was rotational, and it was complement that we defined, yeah. And if there is a whatever metric here, yeah, we restrict metric well, and if this metric is behave well with respect of the action of the group K, then whatever curve that we are looking for can be written in this way. Okay, non-holonomic, and this is just usual Riemannian, and this is the something that is projected to the fiber. Okay, it's better to make a picture. So to find the geodesic here, we had to find the geodesic here that all the time tangent to that guy. Yes. How to produce it? You just take whatever geodesic in the Lie group, somehow they known, and what you do, you project for any moment, you just kill the part that correspond to the fiber. And this is the projection. What you do, you correct along the fiber to the point. From this point, you correct to that point, and finally this curve will be exactly the parallel in all the points tangent to that one. And it will give us, after the projection, the geodesic. Okay. Yeah. And, okay, a little bit more. We come to that equation. Just look at this one. And now, a little bit fluid mechanics. That equation that is written here, when we got it, it would it remind us something. And then, let's see, it's related to that equation that got Arnold when he was interpreting, trying to interpret, to make the interpretation of the Euler equations of in compressible fluid, yes, as the curve in the space of diffeomorphisms. Okay, this is fluid in some manifold. Think that this is Rn. In the space, like a geodesic, in this space with respect of L2 metric. What I'm talking about? So, what is the group of diffeomorphisms on the manifold that is preserve the form? The volume doesn't change under the diffeomorphism, yeah? And there is, it's like, for us, M was just S1, yeah? And the vector fields is just these functions such that they have Lie derivative is 0. It doesn't matter what is written here, but this just means that, so, you see that mu is the fixed point. So the derivative have to be 0. Essentially, it just says you that the derivative of mu is equal to 0. Yeah. So and this is the Euler equation. V is the velocity, divergence, whatever you know what is this. Then if we define the floor, yeah, phi is the floor with the derivative that is defined by the given vector, then apparently this system can be written in this one, in this form. So you see that the second derivative of the floor is nothing more than the gradient. So if you start to multiply it with the whatever element from this Lie algebra, then you come up with the idea that this is have to be 0. And if it is 0, it means that it's minimized this energy function. So it's just the 0 of the derivative of this energy function. Okay? So, and if it is 0 of the derivative of the energy function, it's just a geodesic with respect of what? With respect of metric in that space. In this case, it's just L2 metric. Yeah? L2 metric. Okay. Now, this is just saying you the idea, very quick idea how the Euler equations for the fluid mechanics can be interpreted as a curve that is geodesic with respect of L2 metric in this kind of group of diffeomorphisms. Yeah? Okay. And the differential equation written in the sense of the a joint action of the Lie algebra on the Lie algebra is written in this form. And look, this is our equation. You see, there is this guy lambda that is comes because we have constraint. And if our metric is good enough, then it's just maybe even constant. If not, then it is function of t. And now to finish, I just show you some of the equations that is particular cases. You remember that we have these two parametric families. Yeah? Two parametric families. Now, if we write this this equation in the derivative, yeah, the first one it was Kirillov metric with two parametric. Yeah? This will be written in this form. Okay, it's still complicated. Where alpha beta is this one. Sometimes people call it Hill operator. Yeah, so it's just second derivative with respect of the circle minus constant, Yeah, and if alpha is 1, beta is 0, then this equation that is written here is this one. And apparently, if lambda is 0, this part, it was famous. It's just Konstantin Laxmacher equation. So up to this parameter that appear here because of the constraints, this is the known equation of in the fluid mechanics. Okay, again, it's not so surprised because our government equation was very similar to the equation. And there is some other equations. For different alpha and beta, we can get different other equations, but in this case, we also change the metric. This is not the metric of the Kirillov. This is another metric also with two parameters. It's just Sobolev, you see? It's just Sobolev metric. The product and the product of the derivatives with some coefficients of alpha and beta. So if you change alpha and beta, then this geodesic equation is became like this one, and with the same operator, or concretely for this alpha beta, we have that kind of equation. Maybe I will stop here. There is some other continuation, but yeah.
Questions for Irina?
Hi, no, I can't pretend to understand most of what you're saying, but what I want to know is with the, you introduced these several metrics, right? And you have this geodesic flow.
Yes.
Can you characterize in terms of the evolution of the conformal map that sends the inside into inside? Can you characterize what's happening to the conformal mapping function?
We didn't do this. But actually, this is even in without whatever constraints. You remember that there is this picture, yeah, with conformal map, and then this diffeomorphism. It's actually still absolutely open question how curvature on the shape reflected in the behavior of this diffeomorphism. Yeah, what? Yeah, if you and so on. This is almost nothing is known.
I see.
Even if we forget about these constraints and our things, it's open questions.
There are those people who look at geodesics in shape space based on the Gromov-Post or Gromov-Wasserstein distances.
Yeah.
Can this methodology be put into your framework?
Let's say they didn't use this conformal welding.
Yeah.
They went directly to the space of shapes that's slightly different from what we are considering here. But that's true that they considered. But then, yeah, this works very well if you have the group of diffeomorphisms. If you have the homomorphisms or quasi-isometries, then it's not work so well. Okay, so here essentially that we have the smooth structure diffeomorphism. Yeah, but I know this. This is the works of Mumford and the Michor. I was going through that. Up to some extent, it's probably possible.
In a similar spirit, could this problem be framed as an optimal transportation problem in the sense of Morse and Kantorovich?
That maybe if you know what you transport, if you define the mass that you transport. Then
This is exactly the background
This is
of
the
the
background, yes.
Wasserstein.
I think so, because the Wasserstein is just L2 metric in the space of measures. So if you do this process, then this is just the metric formulation of the optimal transport.
Just a curiosity, you had the slide where there was this stabilizer of an operator. Can you comment on when you were describing earlier, much earlier? Sorry. No, before. And the first time, yeah, here. The next one. So, can you comment on what does it mean? What's the role of there is a kind of Schrödinger operator minus.
This is exactly the operator that finally we actually used in our description. Yeah, it was beta, the second derivative plus alpha. Yeah. Somehow these homogeneous spaces, yes, they are related to these coadjoint orbits that the stabilizers of that Schrödinger operator. Because the Kirillov method, that described in the coadjoint orbits, and these coadjoint orbits they are related to that one.
The stabilizer of what?
Stabilizer of the co-adjoint action on the Lie algebra. Yeah,
and it's that operator. Okay.
If there are no further questions, let's thank Irina again.
Thank you.